Welcome back to The Explainer. I am so thrilled you're here today because, well, we're basically going to become medical detectives. We're looking at this totally fascinating tool that lets clinicians map out the hidden electrical pathways of the human body. By using tiny, controlled electrical clues, we can actually uncover the secret health status of our nerves and muscles. It's like a giant puzzle, and we have the key. So, here's the big question for today. How can we literally see if a nerve is regenerating after a traumatic injury? I mean, we can't exactly peel back the skin and watch a nerve heal in real time, right? But as you'll see today, we can actually unlock this medical mystery using some incredibly simple yet totally powerful visual graphs. Okay, let's dive into this. Our roadmap today is pretty straightforward. We're going to cover 1. Defining the SD curve, 2. Real base and Chronaxy explained, 3. Graphing normal innervation, 4. Graphing complete denervation, 5. Graphing partial denervation, and finally, 6. The pros and cons. We've got it all broken down into easy bullet points, so let's get to it. Section 1. Defining the SD curve. So what is the definition we're working with here? The strength duration, or SD curve, is essentially a graphical representation of the relationship between the intensity of an electrical stimulus and the time taken to elicit a minimal muscle contraction. To explain in easy terms, we're basically just testing two things: how strong a shock needs to be and how long that shock needs to last, just to make a muscle visibly twitch. That's the whole shebang. But timing is absolutely crucial with this test. You wouldn't just jump in and perform an SD curve immediately after someone gets hurt. The optimal waiting period is actually right around 20 to 21 days post-injury. Why? Because that is exactly when nerve regeneration, which follows what we call Wallerian degeneration, might actually start to show some measurable signs. Okay, so let's look at how we actually build the graph of the SD curve. We can explain in easy terms. Honestly, simple enough for a 5-year-old. The vertical axis represents strength or voltage. Simply put, it's just how strong the shock is. And the horizontal axis, that's duration, or time, which is usually measured in milliseconds. That's literally just how long the shock lasts. By plotting these two metrics against each other, boom, we create our curve. Moving right along to Section 2, Riobase and Chronaxy explained. Let's tackle our first crucial definition, the Riobase. This is the absolute baseline strength required to get a muscle response using a very long pulse, essentially an infinite duration. Now, for a healthy person, this normal value usually sits between 2 and 18 milliamps. To give you a real-world example, finding the Riobase for the deltoid muscle in your shoulder typically takes about 14 volts, which is roughly 5 milliamps. Pretty cool, right? And that brings us to our second definition, which is Chronaxy. If Riobase is all about strength, Chronaxy is the specific time factor that's linked directly to it. To find it, you just take the Riobase strength you just found, double it, and then measure the absolute minimum time required to get that muscle to twitch. Chronaxy is incredibly important because it's actually inversely proportional to nerve excitability. To give you a super memorable benchmark to hold on to before we look at the actual curves, you should know that a normal Chronaxy value is less than 1 millisecond. It's tiny. If the Chronaxy is significantly higher than that benchmark, our inner medical detective immediately knows something is definitely wrong with the nerve's excitability. All right, Section 3, Graphing Normal Innervation. In this first scenario, we're looking at a situation where all the nerve fibers supplying the muscle are completely intact and healthy. Because the nerve is doing all the heavy lifting in responding to our electrical stimulus, clinicians actually often refer to this specific setup as the nerve curve. Now, what's really interesting here is the distinct shape on the graph of the SD curve. It forms this beautiful, continuous, smooth, rectangular hyperbola. When you have a perfectly healthy nerve, long electrical pulses easily produce a response at a really low, consistent strength. Then, as the duration gets shorter, you predictably need just a little bit more strength. You'll notice how the curve typically starts its upward rise right around the 1 millisecond mark on the horizontal axis. It's smooth, it's predictable, and it means everything is healthy. Now for Section 4, Graphing Complete Denervation. In this case, it's a completely different story. All the nerve fibers supplying the muscle have degenerated. Because the nerve is totally out of commission, our electrical stimulus is no longer triggering it. Instead, it has to stimulate the muscle tissue directly. So to explain in easy terms, this state is commonly referred to as a muscle curve. And this brilliantly illustrates the difference on the graph of the SD curve. Just look at how incredibly steep this curve is compared to the healthy one, and notice how it's shifted entirely over to the right. Here's the thing. Muscle fibers are way harder to stimulate than nerve fibers. This graph shows us that at very short durations, over on the left side of the axis, you get absolutely no response at all, nothing. To get even a tiny twitch, you have to drastically increase the stimulus strength and keep the duration super long. Up next, Section 5, Graphing Partial Denervation. Now this profile is a real mix. It's basically an electrical tug of war. Some of the nerve fibers have degenerated, while others remain intact, or, even better, they're actively regenerating. When we send our stimulus in, we're getting this combined response. The healthy nerve fibers respond to the weaker, shorter stimuli, while those damaged fibers still need a much stronger, longer kick to wake up. So the absolute crucial point is right where these two different sections of the curve actually meet. It forms this highly characteristic kink. And guys, this kink is literally the visual proof we asked about at the very beginning of the explainer. It shows the exact intersection between the healthy nerve responses and the damaged muscle responses. When a doctor sees this kink suddenly appear on a previously steep denervated curve, they know for a fact that reinnervation and healing are actually happening. It's amazing. Finally, let's wrap up with Section 6, Pros and Cons. Clinicians absolutely love this test for several distinct advantages, which we've laid out in these bullet points here. First off, it is simple, reliable, and cheap. Second, it is incredibly quick and easy to perform. Third, it clearly indicates the exact proportion of denervation based on the depth of the kink we just saw. And finally, it requires very minimal training to actually plot out the graph. However, just to balance our perspective here, we definitely have to note its limits in these next bullet points. The biggest one? It is primarily a qualitative tool, not a fully precise quantitative one. It can also be quite hard to get a clear picture in very large muscles, where maybe only a small proportion of the fibers might actually respond. But perhaps the most surprising fact of all? While this graph definitively tells you a nerve is damaged or healing, it cannot tell you exactly where that injury is located along the nerve pathway. Still, it's just amazing how much data we can pull from a single line on a graph. I mean, if a simple kink on an SD curve can visually prove a microscopic nerve is healing in the dark depths of a muscle, what other hidden physiological battles might simple lines and curves reveal to us in the future? Mastering these visual structures truly empowers our understanding of the human body. Thank you so much for diving into this explanation with me. Keep that curiosity alive, and I will see you next time.